Good morning, everyone. Good morning. Today's video is going to be based on scientific notation. All right, it's going to be a quick introduction on scientific notation. All right, which is going to help us understand how to do math operations when we have different scientific notation numbers. All right, so this is very important and is the base to our next chapter, which is going to be arithmetic with scientific notation. All right, let me share my screen so you can see exactly what I'm talking about. All right. Before we start with scientific notation, I want you to understand what the meaning behind it is. All right. Before we do that, you need to understand what the power of 10 means. Scientific notation is founded on using the power of 10. So whenever we use the power of 10, we're writing big numbers or small numbers as a shortcut. All right. So every time you multiply, we're going to start with larger numbers. Every time you multiply by 10, there will be a shift in place value. All right, which means that the decimal place moves. All right, so for example, if I give you 10 to the 0 equals to 1, 10 to the 1 equals to 10, 10 to the 2, 10 to the 3, and so on and so on and so on. We already spoke about exponents, so we see how exponents are affecting a base of 10. All right, if you have a positive exponent, the number gets larger. The decimal moves to the right. All right, so example, 10 to the 0 equals to 1. 1 is the same thing as saying 1.0. And 10 to the 1 is 10, and so on and so on and so on. So every time my exponent gets larger, my power of 10 gets larger as well. Now, if we have a negative exponent, it's a little different. When we have a negative exponent, you are dividing by a power of 10. So instead of multiplying, when you have a negative exponent, because we already learned the negative exponent rule, which means that we have to do the reciprocal of the number, which is 1 over the number. So 10 to the negative 1 is equal to 1 over 10, which is a tenth. So you are basically dividing by a power of 10. Same thing with 10 to the negative 2 and 10 to the negative 3. To get rid of that negative exponent, we remember that we have to do the reciprocal, and then we could just continue and do the operation. All right, when we have a negative exponent, the number gets smaller. The decimal moves to the left. All right, so you have to remember this. When the number gets larger, the decimal moves to the right. When the number gets smaller, the decimal moves to the left. Now, when we learned that when multiplying by 10, you are just simply adding a zero, right? That's what you learned at the earlier grades. You see when you multiply 2 times 10, it becomes 20. 2 times 100 becomes 200. 2 times 1,000 becomes 2,000. You notice that you are adding zeros. However, that is not 100% correct or 100% accurate. All right. When you multiply by a power of 10, you are moving the decimal point. You're not just adding zeros, you are moving the decimal point. So again, instead of saying 2, I'm going to say 2.0. If I multiply that by 10, which is 10 to the 1, that is equal to 20. The decimal shifted to the right, moved to the right one time. All right. Same thing happens when I have 2 times 100. Or 100 is another way of saying 100 is 10 to the second power. You move the decimal to the right 2 times. That's why you end up with 200. Same thing with 2.0 times 10 times 1,000. We know that 1,000 is 10 to the third power. So the decimal moves 3 times to the right. All right. So keep that in mind. Every time we have a decimal multiplied by a power of 10, we are simply shifting the decimal to the right. Okay, this one right here, I didn't leave just a whole number. I added decimal points. So I have three wholes and 25 hundredths. So when you multiply that by 10, the decimal shifts one spot to the right, you end up with 32.5 or 32 and 5 tenths. All right, same thing happens when you multiply 3.25 times 100. You shift the decimal twice to the right. So you end up with 325. And same thing when you multiply 3.25 times 1,000, you shift the decimal to the right 3 times, and you end up with 3,250. All right. Now, when we divide by a power of 10, we know that the number gets smaller. All right. So, for example, I start with a larger number. 200 divided by 10 equals to 20. 200 divided by 100 equals to 2. And 200 divided by 1,000 equals to 2 tenths or 0.2. And so on with the other numbers. These are just examples. All right. So, again, when we divide by the power of 10, we are not getting rid of a zero. We are shifting the decimal. We are moving the decimal to the left. So if we don't see the decimal, if you don't see the decimal in a whole number, it is always at the end. So instead of saying 200, I could say 200.0. When you divide it by 10, the decimal shifts over and it becomes 20. When you divide by 100, it shifts over 2 times and it becomes 2. When you divide by 1,000, it shifts over 3 times and it becomes 2 tenths or 0.2. All right, so keep that in mind. Before we deal with scientific notation, we are dealing with a power of 10. The power of 10 is going to let us know exactly how to create scientific notation. All right. Now, scientific notation is an approximation. All right. It's not an exact number. Most of the time, scientific notation is an approximation of a very large or very small number. So keep that in mind. Okay. You're not going to have the same number once you do scientific notation. All right. That number is either going to be a little larger or a little smaller from what you already had. That depends on how much you round. All right. So keep that in mind. Scientific notation is an approximation. Now, what do we know? Scientific notation is basically large numbers and small numbers. Now, in the grand scheme of things, numbers are relative to what we're speaking of. For example, if I give you the average height of the Empire State Building is about 15,000 inches. The average height of a tree, sequoia tree, one of the largest trees in the world, is about 3,500 inches. The average height of a human is about 70 inches. All right, so a human compared to the Empire State Building is tiny. But if you start looking at other things, if I say the average height of a cat, about 9 inches, a human is larger than a cat. If I tell you the average height of a fly, 0.1 inches or 1/10 of an inch, you now start seeing compared to other things what is big and what is small. If I get the height of a grain of sand, about 0.005 or 5 thousandths. And if I give you the average height of a pollen grain, it's even smaller. All right, so again, everything is relative. So if I compare a pollen grain to the height of a fly, I see how many place values of a difference they have between each other. And I could say how many times larger that is. All right, so that's what we have to understand. When we're talking about large numbers and small numbers, we have to use the relative to what we're talking about. All right, the number 10 could be considered a very large number if you compare it to the average height of a grain of pollen. All right, now we talk about an atom is even way bigger. So you need to understand again, it's relative to what you're comparing it to. So from now on, from this point forward, any number that is greater than 1, we're going to consider to be a large number. Any number that is less than 1, we're going to consider to be a small number. Now, before understanding scientific notation, there are 2 skills that we need to know. The first skill is place value. We need to know how to identify the place value of a number. All right, so the first thing is we want to find the digit that you want to analyze. You want to look at its position in the number, and then we count from right to left for the whole number, and then every new place value is 10 times larger than the previous place value. So for example, this number right here, if I go from right to left, I know that 1 is in the ones place, the number 2 is in the tens place, the number 3 is in the hundreds place, the number 4 is in the thousands place, the 5 is in the 10,000, the 6 in the 100,000, the 7 is in the millions. All right. Same thing, if I have a small number, the small number goes from left to right because you start with 0. We know that the first digit, 1, is in the 10th place. The second one, the 2, is in the 100th. The third one is in the 1,000th, and so on and so on. When you have a small number, you end up in a TH. All right. So that's the difference. You end up with a TH, and then you have your regular numbers. All right. Make sure you understand the place value because it's going to be very important before we start scientific notation. If you still have more questions about place values, make sure you go back and review it before we continue. Now, the next thing that you need to know before we do scientific notation is rounding. How to round. Rounding depends, again, on the place value and the number you're rounding to. So the first thing you want to do is you want to find the place value that you are rounding to. For example, if they ask you round to the nearest 10, the nearest hundreds or thousands, you have to find the place value. Okay, then we're going to look at the digit to the right of that place value. Okay, we will call that the indicator. If the digit is 5 or greater, you're going to round up. If the digit is 4 or less, the number stays the same. Okay, this is incorrect. You do not round down. I don't know what's that here. Apologize for that. All right. Then if you are rounding, the digits to the right become 0. Okay. And then again, you're going to remove any extra decimals. So for example, if you are asked round the following number to the nearest 100, we're going to find the 100th place. In this case, we see the 8 is the 100th place, right? Then we're going to find the number to the right of that number 8, which is going to be my indicator. In this case, the number 5. And then since it's 5 or greater, we're going to round up. So 78,850, when you round that up, it becomes 78,900. Okay, because that 8 becomes a 9. the rest of the numbers becomes 0. All right, when we're rounding small numbers, this one is round this number to the nearest hundredth. We find the 100th place. In this case, the 100th place is the 5. We look at the number to the right of number 5, which is our indicator. In this case, the number is larger than 5, so we are going to round. So once we round a decimal, you remove the extra decimals. So the 5 becomes a 6, and the number becomes 0.46. You get rid of the extra numbers. You do not add zeros like as you do with large numbers. So again, this is another skill that you need before we do scientific notation, which is rounding. All right. Now, scientific notation. All right, I'm going to give you different steps to determine scientific notation. In this case, all right, again, I don't know what this is 3, supposed to be 4. Sorry, one more time. All right, so again, I'm going to give you 4 steps to solving scientific notation. So first, you're going to find or identify the decimal point. You have to be able to place the decimal point. Where is it in the number? Okay, if the number is a large number and you don't see it, the number is always at the end. All right, the second thing you will do is identify the base. The base is the first non-zero number that you see in the number. All right, and remember that when we read numbers, we go from left to right. When you're reading the number, you're going to find the first non-zero number, and that is part of your base. For more accuracy, we're going to approximate, we're going to include 2 digits after the first non-zero number. So we're going to round to the nearest hundredths. All right. Step number 3, you're going to multiply the base by a power of 10. All right. We're going to multiply the base by a power of 10. And then we have to identify what the power of 10 is. So you're going to multiply the base by a power of 10. And then finally, step number 4 is we're going to determine the number of spaces the decimal will move. This exponent would is going to be for the power. So exponents with a positive or like the exponents will be positive if you're dealing with a large number, and they're going to be negative if you're dealing with a small number. All right. Again, if you don't see the decimal is always at the end. An example is 157. If you don't see the decimal, you know that the decimal is always at the end, because remember, our first step is to find that decimal. All right. So for example, this is one example right here. The diameter of the Earth through the poles is this many feet. So we're going to say it's 41,717,290 feet. We're going to convert this number into scientific notation. The first thing is we know this is a large number because it starts with a whole number. So we know that the decimal is always at the end. If you don't see it, it's always at the end. So step number 1 is find the decimal. Again, if you don't see it, just add it and add a 0 after the decimal. Step number 2 is determine the base. The base is your first non-zero number. If I read my number from left to right, I see that the number 4 is my first non-zero number. Since I want to be accurate, the more digits you use, the more accurate you will be. But I'm going to start using the hundreds place. So I'm going to keep 2 numbers after my base. And then I know that this number 1 right here will be my indicator because I have to round. My base have to be a round number. So I'm going to say 4.17 because my 1 is going to make sure that I do not round this number up because it's less than 5. So I know that my base is 4.17. Then I'm going to multiply that base by a power of 10. So my step number 3 is multiply by a power of 10. And then I'm going to count the number of spaces that the decimal move to identify what my exponent is. Since my decimal was at the end and it moved to after the first non-zero number, I start counting from here. 1, 2, 3, 4, 5, 6, 7. All right, so we know that the exponent will be 7. So if I want to approximate this number in scientific notation, I have 4.17 times 10 to the 7 feet. That is the diameter of the Earth through the poles. All right, now there's another example. The distance from point A to point B is about 146,110 with 7,200 feet. I'm going to convert this number to scientific notation. Step number 1 is to find the decimal. It's right there. You see it. You don't have to worry about finding it. You see it right in front of you. All right. So step number 2 is identify the base. The base is my first non-zero number. When I look at it from left to right, in this case, my first is number 1 is my base. Since I want to be more accurate, I will use the 2 numbers after the base. That means I will have to drop everything after that, so I will round. If I notice my indicator is the number 9, therefore my base, I will have to add 1 to my base. So this number becomes 1.47. All right, so my base is 1.47. Step number 3 is just multiplying it by a power of 10. And step number 4 is counting the number of spaces the decimal moved. Remember, the decimal moved from wherever you will identify it to after the first non-zero number. So count the spaces. 1, 2, 3, 4, 5. So you get 1.47 times 10 to the fifth. All right. So this is how, again, you are going to identify and create scientific notation numbers. All right. So now that you have these 6 examples, you could try that on your own. Pause the video, give it a minute, and then you are going to see the answer in the next slide. All right. Make sure you double check your answers. Make sure everything is correct. If you made a mistake, just go back and identify the steps and see in which step you made a mistake. All right. That's why I gave you 4 steps so you could identify, did I make a mistake in my base? Did I make a mistake in rounding? All right. Did I make a mistake in identifying the decimal point? Did I make the mistake in counting the exponent? All right. So again, the reason why we do steps in math is to identify exactly where you made a mistake and correct those mistakes. All right. All right, so basically the reason why we use scientific notation is to make math easier, okay? This helps us compute very large and very small numbers. Eventually, you're going to be able to do arithmetic, which is basic math operations with scientific notation. But before we do that, we have to make sure that we know how to put numbers in scientific notation, all right? Now, if you look at this number right here, this is called an improper scientific notation. Can anybody think why it's called improper scientific notation? Take a look at it. All right. Now, if you notice, where is the decimal in this number? 236. All right. Is it after the first non-zero number? No, it's not. It's at the end. Therefore, you know that your base is incorrect. The number is supposed to be after the first non-zero number, not at the end. So the base cannot be 236. The base has to be 2.36. So when that happens, what do you think you have to do? How is this going to affect my power of 10? Think about it. All right, so if I just look at the whole number, 236 times 10 to the fifth, and I want to fix it, I want to fix my base becomes 2.36 times 10 to the second power. That is my base alone, if I want to have a proper base. But you also have 10 to the fifth power. So again, now what? What do you think you have to do next? Look at the powers of 10 and remember how we did exponents before. All right. Since 10 to the second power and 10 to the fifth power have the same base, I could apply the product rule, which means that I keep the same base. If they have the same base, I keep the base and I will add the exponents. All right. So 2 plus 5 becomes 7. So I know that this number in proper scientific notation will be 2.36 times 10 to the 7th power. All right. My base got smaller. It went from 236 to 2.36. Therefore, my exponent has to get larger. All right. So keep that in mind. This is very important when you are looking at scientific notation. All right. That was a good segue to this next slide. Okay. Base and exponent manipulation. So if you look at the number 5.28 times 10 to the fifth power, I want to know what happens if my base changes, or I want to know what happens if my exponent changes. Now, I want to keep the number the same. I'm not changing the number, but I want to be able to rewrite this number by manipulating either the exponent or the base. There is a relationship between the two of them, and you need to understand this because it's going to be very important when we're doing arithmetic. All right. Now, if my base becomes bigger, if I start moving the base, if I make my base bigger, I have to make my exponent smaller. All right, that's how that works. If I make my base bigger, my exponent gets smaller. Anytime the decimal moves, it moves is a power of 10. All right, every time the decimal moves is a power of 10. If I make my base bigger by a power of 10, that means I have to make my exponent smaller by that one place that it moved. All right, so if I have 5.28 and I want to make it 52.8, I move my base one spot to the right. I made my base larger by a power of 10. Therefore, I need to make my exponent smaller by a power of 10, by 1. All right, so 5.28 times 10 to the fifth power is the same thing as saying 52.8 times 10 to the fourth power. All right, that is how you manipulate exponents. If you move the base around, you have to move the exponent in order for that number to stay the same. All right. So if I move my base from 5.28 to 5,280, look at what just happened. I move the decimal spot 1, 2, 3 spots to the right. All right. That means that I made my base 1,000 times bigger. Okay. So if I make my base bigger, I have to make my exponent smaller. So 10 to the 5th power becomes 10 to the 2nd power. All right. Sorry for the mistakes. I was rushing to try to get this out today because we're starting scientific notation with our students today. All right, so sorry for the little typos. But again, 10 to the 5th power becomes 10 to the 2nd power because I made my base larger, therefore I have to make my exponent smaller. So 5.28 times 10 to the 5th is the same exact thing as saying 5,280 times 10 to the 2nd power. Again, you are not changing the number, you're just making adjustments so you could have the same number. You're making adjustments so you can manipulate the exponents. All right. Now, if I want to make my base smaller, and this means that my exponent has to be larger. If you haven't noticed, you are doing the opposite. If your base changes, your exponent is going to change as well. So if my exponent becomes larger, my base becomes larger, my exponent will become smaller. If my base becomes smaller, my exponent is going to become larger. So if I move from 5.28 to 0.528, all right, the number is 10 times smaller, then that means that 10 to the 5th power becomes 10 to the 6th power, all right, because I moved the one place value to the left. I made it smaller, therefore I have to make my exponent larger. So 5.28 times 10 to the 5th is the same exact thing as saying 0.528 times 10 to the 6th power. All right, try these problems on your own. Correct the following scientific notation. Make sure that they are, correct them to the proper scientific notation. All right, I want it to be proper. So pause the video, do the 6 on your own, and then we'll show the answers. All right, double check your work. Make sure that your base is the decimal point is always after your first non-zero number, and make the adjustments that you have to do to the exponent. All right, remember my base got smaller, my exponent has to get larger. Okay. All right, so now we know that when we write scientific notation, we do an approximation. All right, but we could also go back to standard form. If I give you scientific notation and I have to put it in a standard form, remember, before people used to think that the exponents meant you add those numbers or zeros. And that is not the case. This is the number of spaces the decimal will move. So if you have 9.13 times 10 to the 10th power, that means that I have to move that decimal over. All right, that means that my base is going to become larger. All right, so how many spaces am I going to move the decimal? 10 spaces. So I start here and I start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, these empty spots get filled with zeros. So if you look at the number, first we wrote the number from standard form to scientific notation. Then we took the number from scientific notation and put it back in standard form. If you look at the original number, 91,287,654,321, that number, when we rewrote it from scientific notation to standard form, is not the exactly same number that we had before. It is an approximation. All right, now you're able to see it. This number was approximated. And again, the more digits you use, the more accurate the number is going to be. But since we only use to the 10th place value, to the 100th place value, then you know that we are not going to be 100% accurate. All right. Now, again, so you have to understand that the biggest misconception is people just add zeros depending on the exponent. That is not the case right now. You know that's not the case. We have to just move the decimal spot. All right, try these numbers again. You are going to get these numbers and put them in standard form. All right, standard form. You're going to take scientific notation numbers and write them in standard form. Take a minute. All right, these are your answers. I hope you check. If you did something wrong, look back at your steps and figure out where you went wrong. All right, very small numbers now. Scientific notation is a method of approximating large and small numbers. We already talked about large numbers. Now we look at small numbers. If you start with a 0, if it's a decimal involved, all right, we are going to consider it to be a small number, even if it's 1/10. If it's a tenth of a number, if it's 0.1, we are going to consider that to be a small number. All right. So in this case, we look at the number, and then we see that we have to follow the rules to put these numbers in scientific notation. All right. So the first thing is to find that decimal point. Luckily for us, when we're dealing with small numbers, the decimal point is visible. We see it is right there. All right. Step number 2 is determine the base. We know the base is your first non-zero number. In this case, going from left to right, my first non-zero number is the number 1. We're going to keep 2 digits after my base, and we're going to round and drop the rest of them. We're going to look at our indicator. In this case, it's the number 7. So our base is going to change because the indicator is larger than 5. So my base becomes 1.24. All right. In this example, the base becomes 1.24. All right. Once you look at the base, you drop everything else. So that was our step number 1 and our step number 2. Step number 3 is you multiply by a power of 10. Since we are dealing with a small number, a lot of people forget to put the negative sign. Small numbers start with a negative exponent. All right. So the first thing you do before you even count the number of spaces the decimal move, put the negative in front of the end, in front of your exponents, so you don't forget to put it later. All right. And then now you're going to count how many spaces the decimal moved. It moved from here to after the 1. So you count the spaces 1, 2, 3, 4, 5, 6. So we know that the exponent is 6. We know it's a small number, so we know it's a negative exponent. Therefore, that number becomes 1.24 times 10 to the negative 6 power. All right. So again, we know that our steps, step 1, identify the decimal. Step number 2, determine the base. Step number 3, multiply by power of 10. Step number 4, determine the exponents. Large numbers, you have positive exponents. Small numbers, you have negative exponents. All right. Count the number of spaces the decimal move. All right. Look at this example. Approximate the following number using scientific notation. Look at the number, find the decimal, determine the base, multiply by power of 10, count the numbers. All right. You have all the steps here in front of you, so you can always refer back to just in case you make a mistake. All right, now do these on your own. All right, put them in scientific notation using small numbers. Take a minute, pause the video. All right, now you can double check your work. See where you went wrong. Again, you have your 4 steps. Look at your steps and identify where you went wrong. Did you go wrong in creating a base? Did you go wrong in counting the spaces? Did you go wrong in making sure the exponent is negative? So again, you can identify where your mistakes were and then fix it. Same thing happens when we have to write them in standard form. So if I have a number scientific notation and I ask you to write in standard form, that means that we are making the number, we're taking the number back to its original form. It's not going to be exactly the same as the first number you had, because again, once we put in scientific notation, we are approximating, but it's going to be pretty close. So we know that when the exponent was positive, the decimal moved to the right, depending on the number of spaces the exponent tell you to move. Now, if the exponent is negative, we are moving the decimal point to the left. All right. So if I have 4.53 and you have a negative 4, you grab the decimal and moves to the left. 1, 2, 3, 4. The decimal goes here. You add your zeros in the empty spot. And since it's a small number, you put a 0 point on the rest of the numbers. All right. So keep that in mind. If the exponent is positive, you move the decimal to the right. If the exponent is negative, you move the decimal to the left. All right. Now convert the following in standard form. Give it a try. All right. Pause the video. All right. Double check your answer. All right. Now, same thing happens if you are given a scientific notation number that is not in the proper form. So if you get 0.0236 times 10 to the negative 5, what can we do about this number? We know that the decimal is not in the proper form. All right. So again, we have to adjust it. So what are we doing to the base? We're making the base larger. We already learned that if you make the base larger, you have to make the exponent smaller. This next couple of slides, I'm going to show you the reason why. All right. So if I have 0.0236 times 10 to the negative 5, we know that my base is not proper. It's not the proper base. The base have to be after the first non-zero number. So in this case, it will be 2.36. So to go from 0.0236 to 2.36, we have to move the decimal over 2 times. 1, 2. All right. Since I make my base larger, I have to make my exponent smaller. So this base alone is 2.36 times 10 to the negative 2 power, to the second power. And you already had 10 to the negative 5. So now what do you do next? 10 to the negative 2 and 10 to the negative 5. Something happens here because the 10 are the same base. Therefore, since they are the same base, I could add the exponents. All right, I'm adding negative 2 plus negative 5, and that becomes negative 7. So this number in proper scientific notation becomes 2.36 times 10 to the negative 7. All right, try these on your own. Pause the video. All right, take a look. Identify where you went wrong. All right, and fix your mistakes. All right, this is the foundation that we need before we could do the operations to scientific notation. Okay. All right, look at this number. Look at the base. Look at the exponents. Now we're mixing it up. You have a large base and a small exponent. So again, the decimal should be after the first non-zero number. It is not. So I'm making my base smaller, which means that I have to do something to my exponents. Remember, if my base becomes smaller, if I go from 361.5 to something else, I need to do something to the exponent, right? So again, I made my base smaller. 361.5 is the same thing as saying 3.62 times 10 to the second power. Now I have to make sure that my exponent gets larger. If my base gets smaller, my exponent gets larger. Don't fall for the trick because you have a negative 5, now you have a negative 3. Remember, when you're looking at the number line, the closer you are to 0, the larger the number if you're looking at negative numbers. So going from negative 5 to negative 3, that means that negative 3 is closer to 0, which makes it larger than negative 5. All right? So be mindful of your base, look at your exponents, and make sure when you add properly. So 2 plus negative 5 is the same thing as saying 2 minus 5, and that gives you negative 3. All right? All right, try these problems on your own. Okay, make sure that you work them out. Make sure that you look at the examples, pause the video, and then you double check your work. All right, double check the work. Okay, so again, make sure that you did all of them right. Make sure you identify when you were wrong. And again, this is the foundation to scientific notation. All right, if you have any questions, make sure that you reach out to me to let me know where you stuck or what other additional information you need. The next video is going to be doing the operations with scientific notation. So that's why this one is very important. You need to master this video before you are able to multiply scientific notations, add and subtract scientific notations, because that is the next step in our learning. All right. All right, thank you, everybody. I know I rushed this one out because I wanted you to have it. I wanted my students to have it today because this week we are working on scientific notation. And for those of you that are not in my school, sorry for the rush. I hope you were able to catch up. And again, good luck and write any comments that you might have in the chat. Okay. See you next time, everybody. Thank you. Bye.